So what could it be? If the baryons account for about 4.5% of all matter density, and the total matter density corresponds to omega of about 27% of the critical density, what are they? They're not baryons. There has to be something else. There are many different possibilities, one of which is massive neutrinos. And these are the only particles that contribute to the dark matter that we actually know exist. But they do not add up to very much. They probably add up to less mass than all mass in stars. There have been many suggestions about possible constituents of the dark matter, and among them, two scenarios emerged as the most likely ones. One is a generic kind of particles called WIMPs, for weakly interacting massive particles. The acronym was obviously play to machos for massive compact halo objects. We do not know what WIMPs would be, but we have some idea what their masses could be. There are theories that go beyond the standard model of particle physics, like supersymmetry, which predict existence of new kinds of particles, some of which could indeed be the dominant constituents of the dark matter. Right now, it is not known which, if any, of those are true, but we're trying to find out. From the accelerator measurements, we have fairly good limits on what their masses can be, and it seems to be that they're at least tens of times the mass of a proton. There is a hope that direct detection of particles responsible for the dark matter will be made in accelerators like Large Hadron Collider, but there are also laboratory experiments trying to detect them directly. I'll talk about them in a second. There are more speculative possibilities of particles not known to exist, but that can be concocted in some way or other. WIMPzillas is one of those. Those would be really massive particles, early thermal remains from the Big Bang. Another generic kind of possible dark matter particles are called axions, and they occur in some of the theories. They could be much lighter, but they can also be massive, and there are also experiments that can be designed to place limits on their density. But there are many other possibilities that have been put forward, probably hundreds. In fact, here is a table from an old review paper, and I'm reproducing it here just to show you the broad variety of the kinds of possible constituents to dark matter. One thing that you can notice if you look through this table, that the mass range of possible dark matter constituents is 80 orders of magnitude, which was simply indicative of our complete ignorance of what they can be. Many of these have been eliminated since then through a variety of measurements, and WIMPs remain probably the most likely kind. Well, what kind of types of dark matter there can be? There can be, and it probably is, more than one type of particles involved. For sure, there are neutrinos, and then there is something else, but that something else may be more than one type of particles. Remember, there used to be only a few chemical elements, and now there are 92. And so there may be 92 different kinds of dark matter, we don't know. But for simplicity, we'll start by assuming there is only one. Now, what can we say about properties of these particles? Turns out that their mass influences the way the large-scale structure in the universe forms, and therefore observations of large-scale structure can constrain physics of the dark matter particles. The basic generic difference is, are there small mass particles which move at relativistic speeds, and that's so-called hot dark matter, or there are more massive particles that then move at slower speeds, which are called the cold dark matter. As it turns out, the hot dark matter leads to structure formation where the biggest structures form first, because all the small-scale irregularities are erased, and we'll talk about that later in class, whereas cold dark matter makes structures form at all scales more or less simultaneously, and smaller ones merge to make larger ones. That seems to be in much better agreement with observations. So nowadays, aside from small contribution of massive neutrinos, the generic belief is that most of the non-baryonic dark matter is of the cold variety, more massive particles. I mentioned the attempts to detect dark matter directly, and there are several of those going on. The idea here is that if you have an apparatus hidden usually deep underground in one of the underground laboratories, in order to eliminate foreground effects of cosmic rays, so properly shielded, and only dark matter can go through because evidently it doesn't interact with regular matter in any other way than gravitationally. Some of the dark matter particles might interact with the material in your detector. These are essentially really high precision bolometers. And the idea here is that simple mechanical encounter of a dark matter particle with, say, an atom of supercold germanium conveys enough kinetic energy that can be in principle detected by this apparatus. So they integrate for a long time. They have to worry a lot about eliminating possible foreground signals. And the only way that you can tell that you are actually looking at dark matter particles is to look for the annual modulation. It's probably a good assumption that the halo of the Milky Way doesn't rotate very much, and sun goes around the galactic center, so there is a wind of dark matter coming through the solar system in the opposite direction of our solar motion. Now the Earth goes around the sun, and so the velocity vector sometimes adds and sometimes subtracts with a 12-month modulation. So if you can see a signal that is modulated in such a way that we see more encounters when Earth's velocity vector is aligned with solar velocity vector relative to the galactic center, and then you see the exact opposite 6 months later, that will be a pretty good indication that you're actually detecting dark matter particles. Claims have been made in the literature by one group to have actually seen such an effect, but none of the other groups can reproduce it. And at this time, it is just generally not believed that detection has been made yet. But it could happen any day. This is a first-rate experimental physics experiment, and there are some very capable people working on it. So we may discover dark matter particles in underground laboratories really soon. Well, the other option is that there is no dark matter, that we misinterpreted gravity, that the law of gravity is different at large distances, or rather at small accelerations. And the dominant of those is so-called MOND, for modified Newtonian dynamics theory, due to Milgram. It is very much ad hoc. It was invented only to explain the rotation curves of these galaxies. As it turns out, it actually runs into problems with observations with clusters of galaxies, or even actually globular star clusters, and its proponents keep tweaking it up. So it does seem to be always adjusted to fit observations for these galaxies and their rotation, but it's always running into some different problem. And most astronomers do not believe that this is a viable possibility. You may think that why is this any less believable than inventing some new kind of particles? But we do know about a lot of different kinds of particles, most of which do not interact electromagnetically. And so why not? It's perfectly sensible. We see gravitational effects that can be easily understood with the presence of the dark matter. And there are many good arguments for its existence, not just the measurements that I mentioned earlier, but there are also implications for structure formation that we'll cover a little later in the class. And so vast majority of cosmologists and astronomers believe that, yes, there is dark matter of some kind. We're just trying to find out what exactly is it made of, and that MOND is not really surviving the observational tests very well. One interesting observation is that the relative fraction or importance of dark matter seems to increase with radius. You may recall that near the centers of galaxies, all of the rotation curve or motions of stars or gas can be explained by the enclosed mass just in stars alone. But as you go to larger and larger radii, stellar density decreases, the relative importance of the dark matter rises. And that's certainly true on the scale of galaxies up to some tens of kiloparsecs in radius. It turns out it extends all the way up to about megaparsecs in radius, and then it remains constant. So once we reach scales of clusters of galaxies or beyond, the mix of visible and non-baryonic dark matter seems to be constant. Next time, we'll talk about gravitational lensing, which is a completely independent way to constrain the amount of a gravitating mass in the universe.